All right, let's get started. All right, PS5 is due tomorrow, or Friday if you take a late day. PS6 is already out, actually, due next Thursday. And then, like we said last time, then comes fall break, and then the midterm week. So I put a lot of information about the midterm up. If you just click on there's an assignment called MT. If you look at it, it has all the details. Bottom line is, this time, on October 17th, is when lecture section 1 will be having its midterm. If your last name begins with A through K, you're directly upstairs. The rest of you are down here. And then, so that's from 3 to 4:20, and then the hybrid section is here from 5 to 6:20 on the 17th. Okay, but there's more information you should read. In particular, you can it's closed book, but you can bring a sheet of notes. So don't worry, don't stress about having to memorize things. Just write them on your sheet of notes, and bring your ID, because we'll be checking your ID when you your university ID when you hand in the exam. So, any questions or problems about anything? Yes?
It doesn't have to be handwritten.
Notes don't have to be handwritten. But I will say that what we often find is the biggest advantage of the sheet of notes is preparing it.
Someone wanted you to repeat it.
Hmm?
Someone wanted you to repeat the note rule?
Okay, you can bring one sheet of notes, front and back, handwritten or printed out, whatever. But if you think that getting a printed copy of your buddy's notes is going to help you, it probably won't very much. The benefit comes when you prepare the notes, in my opinion. Any other questions? Okay. Well, what I've got here is a working version of PS5, and I'm gonna click a button here and generate 1,000 letters, 1,000 characters at level 9. So here I click, and there they are. So those of you that are taking half an hour to generate 100 characters may wonder why this is so much faster. I'm going to talk a little bit about that. How many of you have a solution that takes half an hour to print 100 characters out? How many of you have a solution? Okay. All right. Well, I'm going to talk about that. Okay, let's imagine that this is the book, the text. This is a test, isn't it? And we're searching for the word is. So that's one of the fundamental operations. Is how long does it take? I mean, how many times? You got to find all the occurrences of the letter sequence IS, and you can see that it occurs 3 times up there. So I'll show you the slow way to do it. The slow way to do it is to have a for loop that iterates through the string, and first thing you do is you look at the first 2 characters and see, is that the same as I is? And it's not. So then you look at HI, and then you look at IS. And you found a match, and so you take the character that follows it and put it into your list. And then you continue in that fashion, essentially looking at every index in the string for a match. And there are various ways to do that. But if you see you've written a loop that goes from I to the length, it's probably going to be pretty slow. It just because these books are really long. People think computers are fast, and they are, but a lot of the reason computers are fast is because good algorithms are used. And when you use a bad algorithm, it can slow down the fastest computer. So let me show you a faster way to do it. This summarizes what I just said. Just imagine examining the entire book like that. All right, here's another way. There's a version of index of that takes 2 parameters. So we just don't say, give me the index of the first occurrence of the pattern in the string. We say, beginning at index 0, so this tells it where to begin searching. Beginning at index 0, find the first occurrence of the pattern. And it returns the index. So what is it going to return? Well, it says that. It says it returns 2. So it searched so index of searched, beginning at index 0, found the first occurrence of is, which was right there. So you deal with it. Now what do you do? How do you pick up the search and find the next occurrence of is? Yeah?
Set a substring to the index 0 plus 1.
Okay, so we know that this substring starts at, that is we found starts at index 2. So what we want to do is start searching at index 3 for the next occurrence of is. We just add 1 to that index we just found. And we start searching for the pattern beginning at index 3. And index of will search until it finds the next is. Then, what do we search for? How do we find the next occurrence? Right, we add 1 to the place where the last occurrence was, 5, and we restart the search at index 6. And it'll search through and find the is right there. It's at index 15. So we restart the search at index 16, and that returns -1, which would end the search. Yeah?
So why does it return -1 again?
Okay, the question is, why does it return -1? Who could tell me? Why does index of return -1 when it can't find the pattern? Yeah, back there. Right, that's what the Java doc says. That's just what it does. That's how you know it didn't find the pattern. So this way, if you have a loop, how many times does a loop, each time through the loop you're looking for, you're dealing with a new index. How many times does a loop spin before the problem is over? Does it do it once per character in the text? No. Does it once, basically it does it once per match. Okay? Now, I complained on the previous slide that doing it, one character at a time was slow because you had to, do stuff to each character. But aren't we doing stuff to each character in this solution? After all, what does index of do? Does an index of have to go look at those characters to figure out whether there's a match? I mean, we're not explicitly looking at them ourselves. We're not iterating I through all the characters. But index of has to work somehow. It has to search for is. So how does index of get away with it? Why isn't index of slow? What do you think? Yeah?
Because it can jump so many characters every time.
Well, can it jump so many characters every time? It's not obvious. But you're onto something. That's essentially it. The index of is implemented using a very clever algorithm that's blazingly fast. And it's not an algorithm that you're going to come up with unless you study the problem for a long time. So by letting index of do the work of searching, we end up with a much faster algorithm. So this is just a preview of the sorts of things you consider in CS 2420, where you look at problems to be solved and different ways of doing it and compare the efficiency of different ways of solving. Yeah?
So is the only reason that this way is faster is because someone else wrote the index of method and it's faster than our method?
Okay, so the question is the only reason it's faster is because index of is fast. That's a big part of it. But also, index of does less work than, I'll tell you some of the solutions that I've seen here. So I'm saying you look at that and see if it's, so imagine you do this. You go to the first two characters, you pull them out and create a string from them, and then do dot equals with the pattern. Okay? That's a lot of operations. Index of doesn't have to do that. It's not pulling strings out and making a substring. It's doing the comparisons directly in the string. Okay? So there are various ways that you can, if you took the algorithm that index of used, you could implement this directly without using index of, and yours would be fast too. So the answer to the question is it's faster because index of is a much better algorithm, and also if you do it yourself, you tend to do unnecessary operations. Okay, so where does that leave you? sort of the obvious algorithm that, I've seen a lot of is really slow, so that generating 100 characters out of Pride and Prejudice takes half an hour. Or this faster algorithm, which can generate 100 characters out of, or 1,000 characters I did out of Pride and Prejudice in a couple seconds. So, assuming you've already done it, where does that leave you? Are you feeling blindsided? No one's asking the question I thought they would ask. Yes?
What could we have done to this take a whole 30 minutes? Because none of the programs we've ever made take more than a couple seconds to run.
Well, okay. So none of the programs I've made have taken very long to run. The question is, why does this one take so long? It's because there's a lot of input. Hundreds of thousands of characters to process. And you have to go through those 100,000 characters every time you spit out one character of output. So you scan the entire book, out comes a character. You scan the entire book, out comes a character. So scanning the entire book, it better be fast. Or it's going to be, if you're generating 100 characters, it's going to be slow times 100. You'd rather it be fast times 100. Okay, now, the question I expected people to ask is, if we turn in the slow algorithm, will it cost us any points? Will there be a penalty for doing that? Okay? What do you think? What do you think my answer is? Since you didn't come up with the question, you have to come up with the answer. Yeah? Well, he said, yes, there'll be a penalty because the test cases will take too long and they'll time out. Okay, that's his answer. Does anyone have a different answer? Yeah? Oh, well, I showed you how to do it. I didn't really give you the algorithm, though. And some people already have it done. But it's slow. So, does anyone want to say, no, it shouldn't hurt our grade? Yeah?
Well, I don't think there was anything in the rubric about runtime.
That's right. There wasn't anything in the rubric about runtime.
I think that would be implicit.
So, here's the thing. If yours takes half an hour to deal with Pride and Prejudice, that's okay. We won't take off any points. When we test your program, we won't test it with Pride and Prejudice. All right? We'll test it with a much smaller book. And then it'll be perfectly fine. So if your program's running, if you run your program and you're not patient enough to wait 30 minutes, just go into an editor and cut Pride and Prejudice down to the first chapter and try it on that. And it'll be fast. So don't stress if your program is abysmally slow. In the real world, that would be a disaster. But, we go easy in this class. And in 2420, like I was saying, you really get into this stuff. Learn how to analyze algorithms so in such a way that you could predict the problem in advance rather than just discovering when it happens. Okay? One other place where you can go wrong is when you're reading all the characters out of Pride and Prejudice into a big string. Be sure you use a string builder there, because it can be very slow if you don't. Okay. Okay. So yesterday, or on Monday in here, we talked about collection classes, lists, sets, and maps. You got some experience playing around with them in lab yesterday, and we're going to continue with them today. So suppose I want to know all the words that follow immediately after the word Elizabeth in Pride and Prejudice. All right? Elizabeth occurs, I don't know, say 500 times. I want to know the 500 words, or the words, I should say, that immediately follow after Pride and Prejudice. So what type of object would I use to hold the result? Which object from the collection class? Yeah?
A list of strings.
Okay, so he suggested a list of strings. I said a set of strings. So either answer, it depends on the details of the question, which I didn't specify. What would be the difference between using a list of strings versus a set of strings? Yeah. List can what?
A list can hold repeats.
Okay. Yeah.
A list can hold repeats.
If if you want all, if you don't want duplicates, if you just want to know the unique, distinct words that follow, you'd want a set, no duplicates. If you want to know, all the words including duplicates, furthermore, you want to know the order in which they appeared, you'd use a list. It just depends on what you're after. But we'll use a set here, because that's what I got arranged. So let's try to code that up. Okay, so this is it. I've got the skeleton here. We get a list of words here. So those are the list of all the words in Pride and Prejudice, in lowercase, punctuation dealt with and everything. And we're going to put all the word, we're going to find Elizabeth, and then find the word that follows Elizabeth, and stick it here in this hash set. And then we're going to return the hash set right there. All right? And we have a basically an accumulation loop here that the variable word2 iterates through all words. So every time through the loop, we pull a new word from Pride and Prejudice. If word 1 is equal to Elizabeth, what do we do? So we're looking for all the words that follow Elizabeth. So we've got a word. We're going to assume that word 1 is the word that came before word 2. So assuming that word 1 is the word that came before word 2, what should we do when word 1 is in fact Elizabeth? Yeah?
Add word 2 to the set.
Right. We found a word that follows Elizabeth. Word 2 follows Elizabeth. So we're going to say words.add word 2. Now, is it accurate to say, why do I say that word 1 is the word that, or word 2 is the word that follows word 1? You believe that? Yeah?
Because at the end of your for each loop, you set word 1 to word 2, so when you run it through again, word 2 will be set to the word after word 1.
Okay, so what he said was, we pull a word out, and as soon as we're done with it, that becomes word 1, and then we get the next word out. So as this loop runs, word 1 is one behind word, or one ahead of word 2, if you will. One time through the loop, word 1 is going to be the word, this time through the loop, we've got word 2, it becomes word 1. Next time through, we get a new word 2, it becomes a new word 1. So that's a kind of pattern we haven't seen before. It's an accumulation loop, but we got this extra thing here that's making sure that we know the word, the most recent word that came out is word 1. Now, is this absolutely always going to be the case? That word 1 is the word that came before Elizabeth? It's not.
What was the question?
Is my claim correct? When we get to this point in the loop right here, is word 1 always going to be the word that came before word 2 in the book?
Yes.
Okay, we got to vote for yes. Any other votes? What do you think?
It's not.
I don't think so. I think there's one trick. Yeah?
I guess on the first time, the word that comes before word 2 doesn't exist.
Right.
Yeah.
So the first time through, word 1 is going to be the empty string, and word 2 is going to be the first word in the book. And there is no, in that case, there is no word before word 2. So does the program do the right thing even when we start out with word 1 being an empty string?
Yes.
Yeah, because it won't equal Elizabeth, so we won't put the first word. We can't possibly put the first word into the set because the empty string will never equal Elizabeth. Then we do this assignment, and now word 1 is the first word in the book, and then as soon as the loop runs again, word 2 will be the second word in the book, and then we'll just go down the string like that. So it works. If you're used to mathematics, that may look a little weird. In a math class, that would say word 1 is the same as word 2. But here it means take word 2 and store it in word 1. So for this little bit of time, word 1 and word 2 refer to the same string. But as soon as we hit the top of the loop again, that's changed. We read another word out, and on we go. So let's see what that set looks like. Let's see what I'm doing here. I'm doing problem 1, so that's right. I'll run it. And there they are. These words, these are all the words that follow the unique words. Elizabeth took, Elizabeth read, Elizabeth awoke. So, okay. Any questions about that? It's just basically, we're taking things out of a list and throwing them into a set. Yeah?
So at the bottom, when you're returning words, wouldn't you return word 1 on this method right here? Wouldn't you return word 1?
Okay, so he's asking, I'm returning words, shouldn't I be returning word 1? Well, I'm supposed to be returning a set of strings.
Oh.
And this is not a set of strings. This is an accumulation loop, fundamentally. So that's our accumulation variable. In here, we modify the accumulation variable. Here, we return it. This here is our little twist. So yeah, we want to return the set, because that contains the answer we're trying to build up. Any other questions? All right, well, let's look at another problem. All right, there we created a set of all the words that follow Elizabeth. I want to do something different now. For each word that follows immediately after Elizabeth, I want to know how many times it does so. So some of those words that we saw displayed occur only once. Some of them occur 3 times. Some of them occur 2 times. So I want to know which words occurred and how many times. You got a question?
Yes, so sorry I was a little late to the punch. I do have a question about the previous, about the one we just finished. That I noticed that every word we see that comes after Elizabeth is a regular word. But when we were listing all the words on Monday, many of them had punctuation.
Okay.
Or after them.
Right. So she's pointing out that these words are, look normal. They don't have stray punctuation as part of them. That's because at the very end of class on Monday, and I was kind of rushed, I modified the program to take care of them. And
it did, but it still had the problem of having apostrophes.
Well, I fixed that. I fixed everything. So we'll look at that again later when we get back to that part of the program. Okay, so I want to know how many times each word, I want to know what words follow Elizabeth immediately and how many times it occurs. Each such word occurs. So think about that. Take 30 seconds, talk to the people around you. Tell me what type of object do I need to hold the result? Am I after some sort of list, a set, a map, whatever? Okay, who could tell me what type of object we need to hold this information? Over there. A map. Okay, so a map is good. So what's the key? What type is the key? What type is the value? Remember, you look up and store by value. So yes?
Maybe string and an integer.
Okay, so that's right. So we need a map from strings to integers. So it's going to map every word that occurs after Elizabeth to the number of times it occurs. Yeah?
Could you use a 2D array?
Could you use yeah, you could use 2 arrays. You could use an array of strings and then an array of counts, where the key is in the string array and the counts in the int array. But why bother when Java provides maps? You don't have to, you're basically building your own map when you do that. In Java's, yeah. Java does something for you, you should use it instead of trying to, you're not going to improve on it, most likely. Okay, so we use a hash map or a tree map? I've got to vote for hash map, yeah?
Yeah, that's right.
I mean, it really doesn't matter that much. Hash maps are slightly faster. Tree maps will put the words in sorted order. So it just depends what matters to you. I think I used a hash map just for variety because I was using tree maps Monday. So let's go look at the method I've written here. So I create the empty map right here. I'm using that same trick, so I got word 1. So the program is the same as program 2, except what goes on inside the if here is different. That's really the only difference. You know, it's the same deal. We're down here, we assign word 2 into word 1. We return the data structure here. So all that differs is what we do when word 1 is Elizabeth. And you can see I've broken it down. I've said if word 2 is not a key, I do something here. If it is a key, I do something there. So either we've seen word 2 before, we've already got it, it's already a key in the data structure, it's already been counted, or it's the first time we've encountered that word, it's a brand new key. So we're going to do something different. Okay? So take a minute, talk to people around you, figure out what do we put right there where it's highlighted. What code do I do? What operation do I do when I encounter a following word for the first time? All right. Who can tell me what do we do? Go ahead. Okay, say it louder. Okay, so we're definitely going to modify word counts. Okay. So what is the idea is we have this word. Well, to this point, how many times has this word occurred in the following Elizabeth?
0.
Well, including this current time, 1. We've just discovered the first time it occurs. So we need to put word 2 as the key and 1 as the value. So if we look it up at this point, we'll find out that word 2 has occurred once. Yeah?
So can you explain the difference between .put and .add in reference to hash maps?
Well, okay, so .put adds a key to the table and associates it with the value. It adds a key to the map and associates it with the value, maps it to the value. If it already existed, if there already was a key value pair in there, it gets replaced. Okay? And you ask, what does .add do? There is no .add. .add is an operation on sets and lists. Okay? But here it's called put because you're not adding one thing, I guess. You're putting a relationship in. I assume that's why they named it that way. Okay, so that works. Now, what if it turns out that word counts does contain the keyword 2? We end up here. We've seen this word before. So maybe the word has occurred 4 times. So that means that in the hash map, word 2 will be mapped to 4. When we're all done with the code that needs to go there, what will word 2 need to be mapped to? 5. To 5. So what I need code here to do is to change what word 2 maps to. So that it maps to something 1 bigger than before. I don't want an answer right now. I want you to talk about it for 45 seconds or so. Figure out what line of code I need to do. I'm again going to modify word count. Okay, who could help me out? What do we do? Okay, you can go now.
You would do the word count stuff, but and then you would do word 2 as like.
Okay, so we're putting in a new mapping for word 2.
And then the second one, you do word count dot get, and use word 2, and then plus 1.
Right. So this is what he said. So we are mapping word 2 to the current value of word 2 plus 1. So what this will do is go in and get out the integer that word 2 maps to. We know it maps to an integer, or we wouldn't be in the else. So out comes the 4, perhaps. We add 1 to it, giving us the 5, and then that gets stored back into the hash map as the new value of word 2. Okay? So if we run that, I have to go change it up here, so I run problem 2. We should see a map come out. Okay, so silently occurs twice, half occurs once, fault occurs 3. Here's one that came 7. Where'd it go? Would. Okay, so it seems to be working. So there we have another example of code that manipulates a hash map, or a collection, a class object. You'll be surprised as you go on at how many problems boil down to using classes from the collection, one of these 6 collection classes. And if you're not good at recognizing how to use them, you end up writing a lot more code than people who are good at recognizing when to use them. Okay? Question, yeah?
What could I be doing wrong if mine doesn't seem to be doing that?
Well, so the question is that her program isn't doing this, what's wrong with it?
It's only, yeah, so it's just listing off the words with no number.
Yeah, well then you're probably not using the hash map. I'd have to look at it, I can't. Lots could be wrong there, so. I can look.
Do you have to comment out the hash step before you do the hash map?
No, I think what you probably do is you're calling problem 1 instead of problem 2 up here.
Oh, probably. Yep.
I guess I can solve it without looking at it. Any other questions?
Yay, it worked.
Okay. Let's look at problem 3. Okay. Now, for every word, not just Elizabeth, for every word in Pride and Prejudice, so imagine there's a word W that occurs in Pride and Prejudice, I want to know all the words that follow immediately after that word. So like, for Elizabeth, I want that set that we got before, the set of words that followed it. But I also want for the, what are all the words that follow the? What are all the words that follow Mr.? Okay? So the question here again is, what type of object do I need to hold the result? Okay, all right. Put your heads together for 30 seconds, see if you can come up with an answer. This is where you learn how to take advantage of those collection classes. Okay. How about someone that hasn't answered yet today? Anyone brave enough to put themselves on the line a little bit here? There's no penalty. Yeah? Well, so it sounds like you're explaining how to do it. But what I want to know is, what are we building? What will our method return? Yeah. Okay, so the suggestion there was a map from strings to strings. Okay? What do you think? Okay? Would be what?
I would do a map of strings that go to a set.
Okay.
Of strings.
So the other suggestion is map something that maps from strings to sets of strings. So the thing to realize is, a map from string to strings, we can only associate one word with every word in the book. But we got to get a set of words involved. So that's how we do it. A map where you give it a string and out will come a set of strings. The set of strings that follows the key in the book. Okay? And of course, we got to decide, do we want hash map, tree map, hash set, tree set? I just use hash versions just because. Any questions about that choice? Oh, yes.
Just how do we know when it stops? Instead of like, if it gets a word like the, and then it just repeats the rest of it. Like doing that. Doing to, like, if you're going to another set of strings, like how does it not, like, you know, store the rest?
In the same set?
Yeah, if that makes sense.
Okay, so you're basically asking how the code will
Like stop at a
will
certain
stop. Let's look at the code and see it there. Okay, let's go. Let me change it up here first. Okay. It's the same familiar structure. It's, again, it's just that if in the middle that's different. And it also, I mean, the well, I guess that's not quite right. It's all this stuff that's different. But it's the same basic structure that we're just walking down, looking at words. So up here we declare the hash map. We declare word one like we always have. Here, what's going on right there? Yep.
I don't know, maybe that's just like the map that we would put, or the set that we would put like in the parameters of the like,
Okay. Well, first of all, what is all following words?
What do you want to return?
Yeah, all following words is our hash set. So what question are we asking here? Yeah?
Is word one already in your map?
Right. So we're looking up word one. And we want to know, is it already mapped to some set? Because the first time we find a word, we're going to have to put a set containing the word that follows it into the map. But other times, if the word already maps to a set, we're going to have to update that set. So we're just trying to figure out, we're getting the set to which this word maps. If it maps to null, that means this key here was not in the set already. If it doesn't map to null, we do something else. Let's start with this one right here first. So we've just gotten a word like Elizabeth. We look up Elizabeth in the map we're building, and we find out that we already know that Elizabeth maps to said and walked. And now we've got a new word, 8. What do we do with that new word? What do we do with the new word? How do we, just in terms, you don't have to tell me the code. Conceptually, what do we do with this new word we just found? We already know the words, the words that we know so far that come after Elizabeth are right there. So what do we do with this new word? Yeah. Yeah. Add it to word set. So if we've already got a set, we pulled it out right here, so we'll just add this new word to it. Okay? What if this first time we've seen this particular word, so it's actually not in the map yet? This is the first word, first time we've encountered this word. What do we need to do? What should we have? Yeah.
You need to add it to all following words with the key and then the word that you found.
Okay, so what he was saying is we need to change word set. I mean, what's it called? All following words. We need to put a new mapping in. So we got to map word 1 to something new. Okay? So in this case, word 1 already mapped to something, to a set, and we're just adding to that set. Here, it's the first time we've encountered word 1, so what do we put here? What does that need to be? Does it need to be word 2? Yeah? Okay, see, okay, this doesn't work because this here is a string, and it wants a hash set of strings. We need to create a set, a new set that contains word 2 and add this here. So we'll call that singleton. So we need to create a hash set.
Can you not initialize it?
Okay, how would we create this hash set that contains just the string word 2? Okay, ask a different question. How can we create an empty set? Yeah? Right. We just create a new hash set that's empty. Then, how do we make it so it's a set containing word 2?
Add it.
Yeah, we just say add word 2. So we create the set that contains word 2, and we put it into the hash map. So now this word maps to a set containing word 2. Yeah?
So this is actually the question I had in the lab this week. Is there no constructor for like hash set string where you can just pass it one string and it'll initialize with that?
Okay, so he was saying it would be nice if there were a constructor to which you could do this.
Yeah.
But there isn't. There are constructors, if you have another set or another list, you can pass the whole list in, but no, there's not. So we have to create the empty set, then we add a word to it, then we add it to the set. Now, this is a lot like the last solution. Remember this one? If we never saw it before, we stored a 1. If we had stored it before, saw it before, we got the integer out, added 1 to it, and put it back in as a new value. Here, if we have not seen it before, we can't just store a 1. We have to create the set we need to store in there, and then we store it. And then, in this case, it's really simple. We have the set. We just add word 2 to it. Yeah?
In your singleton initialization, why didn't you pass it the string there into the function?
Okay, so in the singleton initialization, why didn't I pass it to string here?
No, in generic.
Oh, here?
Yeah.
Okay, he's asking why did I do that instead of that?
Yeah.
Because it works to not do it. It just saves typing. So in situations like this, when it can tell, you already said you want a hash set of strings. You can just leave that out and it fills in the blank for you. That gets really useful like up here, right, where I'd have to take all that stuff and stick it in there. I did handsprings the day that Java added that feature, at least mentally. Okay, now there's a subtle bug in this code that you might not even find if you ran it. Yeah? Right. The very first time through the loop, it's going to take the first word in the book and it's going to map the empty string, which is going to be word 1, to that first word in the book. Right here. So what we return here is going to be all following words is just right, except it has an extra mapping that we don't want. It maps the empty string to something. So one approach would be to think harder about what's going on up here so we don't do that. You know, we could say something like, we could say if word 1 is equal to, equals empty string, or don't do any of this stuff. The other thing you can do is just fix it up later before you return. And that's easy enough to do. So what I'll just do is, all following words dot what? What should I do? How can I fix this thing up so it no longer contains the mapping from the empty string to the first word in the book? Yeah? Well, delete's a good guess, but it's actually remove. So we remove what? You have to give it a key. Yeah? Yeah. We tell it to remove that key and its value from the map. That just eliminates the problem, and then we return. So now when we run it, it'll be, you probably wouldn't have noticed it in the first place. But that's what it, so that's showing you that nicely is followed by we, acutely is followed by Elizabeth, more painful did, and so on. And if we skip ahead and see what Elizabeth, well, I'm not going to get there very fast. Elizabeth follows a lot of things. But somewhere is the mapping that maps Elizabeth to a set that we figured out in problem 1. Here.
Look for Elizabeth equal.
Ah, yes. Elizabeth equals. There we are. So this is a set that we've seen before. You know, it's hundreds of words long, so I won't. Okay? So this has just been more practice with lists, sets, and maps. Really important stuff. Use them all the time. You study them to death in 2420 when you learn how to create things like hash tables and binary search trees. And linked lists, dynamically growing lists. Okay, let's take a quick break and then we'll push on. All right, let's get started again. So at some point in the last 45 minutes, my mic went out. Did you notice when that happened?
Yes.
You got to tell me, because I can't tell. This is like the third set of batteries. I think they gave us a bunch of bad batteries upstairs. Yeah, I'm sorry about that. Okay. Let's think about what we just did. So I want to visualize, in a sense, what's happening in memory when we execute this code. So we create an empty set, and then we go through a scanner, and we take each token, convert to lowercase, and add it to the set. That's what that code does. So there's our set. And we're going through the string, this is a test is. Okay? So go through the loop, we pull out this. What's going to happen? What's going to change about that set up there? When we execute this all words.add right here. Yeah.
It's going to add this to this.
Right. This will show up. All right? Then what's going to happen when we add is? Is shows up. Shows up. Test shows up. What happens when we do again? Anybody want to make a bet? Yeah.
Since it's a set, it won't add another A.
Right. It won't add another when it's already there, so you wouldn't see any change. And then is wouldn't change it either. That's just what a set is. Now let's look at this one. Now I'm creating a map from strings to integers. And this is sort of like the code we wrote. It gets the next word. So word counts is our map. If word counts already contains that key word, it's going to put a 1 into it. Otherwise, it's going to update the count to something new. That's the exact code that we used earlier. So here's our map. And we're going through this is a test is. So when we encounter the this, what's going to show up in my map? Yeah?
This equals 1.
Right, this will map to 1. Right? We encounter it for the first time. This is not in the map, so it's going to map this to 1. Okay? What's going to happen when we find is? Yeah? Yep, is maps to 1. Then what? We get that. We get test. Now, what happens when we encounter the A again? We'll be down in this case. So it'll go into word counts, pull out the value of A, which is 1, add 1 to it, and store it back. So the mapping changes to 2. And similarly with is, the mapping changes to 2. So the thing to realize is all these operations modify the existing map. A map is mutable. It's changeable. They're operations that add things and remove things from it. Unlike a string, there are no methods that can modify a string, go in and change one character to another. Okay, now, let's suppose this is our input here. The map that we just created is our input. And I want to reverse it so that the integers become the keys and the sets of words become the values. So I want to know what words occur once. So I want 1 to map to this, the set containing this and test. I want 2 to map to the set containing A and this in a new tree map. So here's our map. That's the tree map we're creating. And we just go through every, well, look at this right here. What is this for each loop doing? What's it iterating through? Yeah?
The set of keys.
Okay, so it's going through the set of keys. So that's a common way to iterate through a map, is to iterate through the keys. So we're looking at all the keys in the map. We are, now I went too far there. We're getting out the number of times that word occurs. I'm sorry. You tell me, what's this line of code doing? Yep.
It's storing the integer that key is
Okay. So what he said was, it's going up to word counts. Let's say that we got this out first. So it's just looking up the number of times, it's looking up the integer that this is mapped to, and storing it in this variable count. And then the next thing we do is we look and see if this map knows about count. And if it, which that wouldn't pop up all the time. So it does count map.get of count. And if that's null, which it will be the first time through, it what happens right here? As soon as that disappears. So if, when we look up in count map, when we look up in there to see if this particular count has been seen before, we found out that it hasn't. What are we doing right there? Yeah? Right, we're mapping count to an empty set. And then, now we're sure that count maps to something. Either count's going to map to this empty set or it maps to what it did before. So we come down here, we pull out what count maps to, which is some set, and we add the word to it. So let's go through the code and go through and see what happens. So the first thing that happens is we, I guess my code first pulled out a 2. Since it didn't know what, it never seen a 2 before, it mapped 2 to an empty set, but then what's it going to do? So we've gotten to this point. 2 is in the key set of, 2 is in the key set of word counts. Now what do we do? What's this line of code going to do? Yeah?
It's going to associate whatever word from the other set or the other map sort of associate with it.
Okay. So it adds the word to the set. All right, so let's back up. We're going through this iteration. We're looking at the keys in the word count set. So we're looking at the keys up here, 2 and 1. We get the, well, we're looking at the keys, which are the strings. So word in this case was We found out that occurred twice. We come down here and we see that the twice isn't a key in the count map. So we make it map to that empty black cloud. And then we add to it. Okay? Okay. Next time through, let's say the next key we get out, let's say is. Okay, we'll find out that that is maps to 2. We'll notice that 2 is already known in this map, and so we'll just add is to what 2 maps to. So we modify that black cloud. Next we encounter test, which maps to 1. So we're reversing things. We have 1 map to test, and then when we get this, we get it becomes like that. So that's the conceptual structure of what we're building. Yep.
So how does the program know that this certain word is mapped to the actual key without actually specifying it in this code right there?
Well, this map is the input, and this is the key set of this map. And we're just going through the keys. We find out that is maps to 2, so we make sure that 2 maps to a set containing is. We make sure that A maps to 2, so over here we make sure that 2 maps to a set containing A. And similarly for 1. So when we're all done, we've sort of reversed the roles of the keys and the values. But this picture is misleading. If this is your picture of how sets and maps relate to each other, how they look in memory, even abstractly, it's a little bit misleading. Let me explain why. What is stored, when you have something that contains an object, when we say something contains an object, it actually contains a reference to an object. So the key 2 refers to a set that's floating out there somewhere. The key 1 refers, it has the address in memory of the actual object that's somewhere else in memory. Yeah?
Is it the key that refers to those, or is it the value associated with the key?
It's the value associated with the key is a reference.
Okay.
And in fact, the key itself is a reference to the key object. Okay? Because that too is actually an integer object. But I don't have too many errors floating around. Okay? And the thing to realize is objects can be shared. When you go and you get, suppose you said, give me the set to which 2 maps and store it in the variable set. You do not get a copy of the set. You get a reference to the set. So that now the map is referring to the same set as that variable set is. That means if you have if you've got this variable set and you say set.add hello, that black cloud will change to hello. And so now 2 is still mapping to the same set, but the set has changed. So references can be shared. When you assign, if you have a set that's stored in a variable x, and then you store x in another variable y, you have not made a copy of x. You've made a copy of the reference. Both those variables are going to refer to the same object. If you say x.add, the change will be visible through y. Strings are objects too. So actually what's stored in those sets of strings are not actual string objects, but references to string objects. But strings aren't mutable. There's no method that can modify a string. And so the distinction between having an object in a reference to the object isn't really important with strings. It's only important with mutable objects. So we can simplify the picture. Right? There's no method to set the ith character of a string to some other character. Okay? So it's important to remember, we'll come back to this again and again, that what are stored in reference variables are references. And you often end up with multiple variables referring to the same physical object. Copying, a lot of students want to think that when you take a set, you store it in a variable, it's copied somehow. It's not. It's the same set. If you modify it here, it'll be visible there. Okay, now I want to go back to where we were last time. So we had worked on some methods to analyze words, so let me get down to it. Okay, so this was sort of the root one. This was the one that takes a scanner that's connected to Pride and Prejudice or whatever, and returns a list of all the words, reduced to lowercase. And so someone remind me, why did I do that? What problem did I solve by doing that? Yeah?
You said like everything that's not lowercase to lower, like you change what classified like a space or a line character. So you
Okay.
have to deal with all the
Right. So what this did was it changes the scanner's notion of what characters are considered white space, if you will, the delimiters between tokens. So normally it just treats white space as the delimiters, and tokens are everything that's separated by white space. But here we're seeing everything is separation, except for letters, digits, and symbols. So it treats commas and periods and such as stuff to be thrown away, not parts of tokens. Okay? What did this code right here solve? Yeah?
Remove the quotation marks in front of.
Okay, so because we're treating quotation marks as something important, if there's single quotes around a word, like hello, imagine hello in single quotes, it'll be part of the token. And so what this loop does is it removes all leading single quotes. So it's just saying if a word starts with a single quote, remove that single quote. And keep doing that until it doesn't start with a single quote. What about this loop here? So it's saying if the word ends with a single quote and the next to last word is not an S, then remove the single quote. Okay? So I'm trying to preserve contractions and possessives. And then finally, if the word consisted of nothing but single quotes, I now have an empty word, an empty string, and I want to throw it away. So anyway, that's what gives us a nice set of words, without lots of periods and quotation marks and such. Okay? This was a method that took in a list of words that we just got and creates a string, a set. And one easy way to do it is like that. You just take the list, pass it to the tree set constructor, and voila, you have a tree set. You don't have to write a loop. This just converts a list of words into a set of words. And here's one we want to write. I want to map every word in the list to the number of times it occurs in the list. You seen that problem before? Yeah, we did a very similar one, almost identical before. Okay? So how can I arrange so that this word count maps every word to the number of times it occurs? Okay. I've got to do some looping here. What am I looping over? What am I consuming in my loop? Yeah?
The array list string words.
Okay, I'm looping over this list of words. So let's do that. For each word in words, do something. All right, so each time through I'm grabbing a word out of the list. What do I do with the word? Go ahead. Well, okay, so I've got to change word count because I've just seen an occurrence of this word. Yeah? Okay, I need to find out if it's already, if I've already encountered this word before. So I'm going to look at if word count dot contains key. So if we've seen this word before. So we've either seen this word before or we haven't. Okay? Suppose that this is the first time we've seen the word. What do we do? Yeah? Say it a little louder. Okay, so we're going to do, it's the first time we've encountered it, so we're going to put word 1. So we've seen it once. What was that? Oh, you're right. I need to change the sense of this. Okay. What if we've seen it before? We've seen exactly this pattern before. Yeah? Right. So we've got to change what word maps to. So before, it mapped to word count. This is what it maps to right now. So maybe it's been seen 3 times before. Now it's that many times. Okay.
Word count output.
Thank you. No, that's right.
At the beginning. Word count.
Very good. Okay, so we either map it to 1 or we map it to 1 more than what it's already mapped to, and then we return. So let's so you can see I used a tree set here. So you can see all these words here. You know, won't occur once, witticisms once, with 1053, and so on. Okay, that's very similar to one we've done already, and this next one is pretty similar as well. This time I want to do that reversal I was talking about. Given a set, given a map from words to numbers, I want to turn it around so it's a map from numbers to set of words. So I need to bring that console back up, so I'll just run the program again. So for example, youths occurs once. Yule occurs once. York occurs once. So what I want to do is create a set where create a map where 1 maps to a set that contains York and Yule and youths and rights and wretchedly and worthlessness and every other one that occurs once. So 1 needs to map to the set of all words that occur once. 2 needs to map to the set of all words that occur twice. Yeah? Okay? So this is what this thing has to do. It's going to create this map from integers to sets of strings so we can find out what's the champion word, how many times does it occur. So what do we do? What do we need to iterate over? Yeah? Pardon? Okay, right, we're going to iterate over the key set of the existing map. So we're just going to do for each. So the keys in the existing map are strings. Let's iterate over all the keys. And what did I do wrong? Word count. Okay. So I encounter a word. What should I do with it? How many times does that word occur? How can I find that out? How many times does this word occur in that map? Yeah?
Word count get.
Right. Word count dot get word. All right? That's how many times it occurs. So I won't count to map to a set that contains word. So I got to break it down in 2 cases again. Either we've seen this count before or we haven't. So if word frequency already contains a key, count, I'll do one thing. Let's say if it doesn't contain it, I'm going to do one thing. Okay, what am I going to do? Yep. Okay, we need to have, at a minimum, we need to have word frequency, map, count to an empty set. Spell it wrong, F-R-L. Okay, so I just arranged for count to map to an empty tree set. All right, so but when I get to this point in the code, I'm guaranteed that count maps to a tree set that doesn't contain the word. So it either already existed or I just made it exist. Either way, what do I need to do? How can I've got to take care of adding this word right here to the set that count maps to. How can I add word to the set to which count maps? What is the set to which count maps? How do I calculate that? Yep.
Word frequency dot get.
Yeah, it's word frequency. I look up word. I'm guaranteed to get back a set. It may be the empty set that we just associated with count. It may be an old set that was there already. But either way, I need to add the word to it. So how do I add a word to this set? Yeah, the add method. Okay, and we already saw the picture for this. When we get the set out, we don't get a copy of the set. We get a reference to the same set that's stored in word frequency. So that when we modify it here, it's modified, the version that's referenced by the map gets modified. Oh, it isn't like that. Yeah. Okay, so we're getting them. We're pulling out the set to which count maps, and then we add the word. Yeah.
So I just kind of got lost on what the variable count actually does or how it works.
Okay. What's coming in is something that maps words to the number of times the words occur. Okay. So it's going to map Elizabeth to a big number. It's going to map the to a bigger number. And then I'm just turning it around so that the numbers map to the sets of words that occur that many times. So when I run this, I find out that 4,331, which is the biggest key, maps to the set the. So that tells us that the occurred 431 times. In the original set, in the original map, the mapped to 4331. 2 mapped to 4163. Win and Darcy both map to 374. So in this new one, I have 374 mapped to the set containing Darcy and Win. So since it's a tree set, everything is sorted, tree map, and I can find out, the common words or the uncommon ones. If we go back up to the end of this. All right. These are words that occur 4 times each. I don't know what happened to the ones that... It's kind of weird. Somehow there seemed to be a hiccup in the display. It let out the 5, the 1, the 2, and the 3. But anyway, we sort of reversed them out. Okay? This takes some practice to get the hang for it, so hopefully you learn a little bit on this current assignment and some on the next. Let me in here.